Good morning. Hi. My name is Gannot. I come from Bar-Ilan University. I'm part of the SPRING Consortium. Welcome to the audiovisual session of this morning, of this early morning. So I will speak later, but first let me introduce Professor Wenwu Wang. Professor Wang is from SoRAIM University in the School of Computer Science and Electrical Engineering, but also the AI Center of the Institute of the university. Wenwu did a lot of work in audiovisual and audio separation in general, hundreds of papers, you might say, a lot of prizes. Also took a lot of leadership roles as an associate editor, as a chair of committees and so on. And we are excited to hear about your work on audiovisual. So thank you for coming.
Thank you very much, Sharon, for the nice introduction. And also thanks, Xavier, for inviting me here. And today I'm going to talk about audiovisual speech source separation and speaker tracking. So the work on audio-visual speech source separation is a little bit out of date now, but this is one of the earlier work we have done here. But recently there's a surge of interest in audio-visual speech source separation. So this is the outline of my talk. I will cover a few topics, but obviously the time is limited, so probably in the high level, some details in the papers. So I start with audio-visual speech source separation and then move on to multi-speaker localization tracking. And we also briefly mention the ongoing work on ego-centric audiovisual speaker localization tracking. This is the work we have studied last year. And also, and finally, we conclude and discuss potential future works. The problem we started probably 20 years ago is on this so-called cocktail party problem. So cocktail party problem was coined by Professor Cherry from Imperial College in 1953. So the earlier version of this problem is called ballroom problems by Hermos in 1863. So the problem is, if you briefly describe that, it's like a human has the ability to focus on a single conversation in a very noisy cocktail party environment, but it's pretty challenging for machines to do the same thing, right? For example, if we have multiple speakers talking in a room and with some interfering sound from music, from some other background sound, then how machines, for example, robots, are able to concentrate or understanding the particular target voice with the presence of so many interfering sound there. So if we really dig into this problem, then it potentially can involve several tasks. For example, we need to detect where they are and localize or track them, or who is speaking and when. This is to do with speaker diarization and multi-speaker talking environment. We have to, for example, separate individual sound sources and automatic speech recognition if we really want to understand the particular voice. And also potentially understanding the environment, what are the acoustic scenes and events in the environment, and what type of room acoustics properties. So there are many things we need to consider, right? Here, of course, we focus on localization and tracking and also separation. So this is the statement made by Professor Cherry in 1957. Nowadays, I think this problem is still pretty open, especially for some of the challenging cases. So speech source separation, this problem has been studied for many years now. So if you look at the literature, there are many techniques out there, beamforming based on the spatial information. You estimate the, for example, the steering vectors, and blind source separation, independent component analysis. They're based on statistical properties of the signal. You try to explore some statistical property like independence. If the source is coming from different speakers, we can assume that they are independent statistically. And speech enhancement techniques only works for the noises following particular type of property. For example, some kind of white Gaussian noise or non-stationary noise becoming more challenging. So this is limited to some certain type of noises. And sparse representation matrix factorization that also has been applied in this context, especially if you want to separate a smaller number of sources as compared with the number of microphone signals. And computational auditory scene analysis, in particular, this time frequency masking technique has been extensively studied. That's actually based on analyzing of the temporal and the spectral properties of the mixtures. And you try to figure out each time frequency point belonging to which sound source. And recent few years, as you can imagine, deep learning is given a state-of-the-art result, but this requires training data. And a lot of classical techniques, they don't necessarily need any training data. So there's pros and cons when you apply these techniques to this particular problem. So I pick up probably two classical techniques. One is ICA, is independent component analysis. For example, this is a simple cases where you have two unknown speech sources and which are mixed together into two microphone signals, and how you design the separation algorithm to be able to estimate the sound sources S1 and S2. Here we denote it as Y1 and Y2, which are estimated version of S1 and S2. So here, both S and how the sound sources are mixed together into the mixtures are unknown. So this is conventionally we try to develop a separation system, for example, based on independence assumptions, which we can then use some criteria in statistics. For example, high order statistical curtices. We can try to to maximize the independence between the estimated sources Y1 and Y2. Another technique is also quite popular. It's called time frequency masking. So here, this is, for example, time frequency representation, for example, a spectrogram of the mixture. And this is time frame, and this is the frequency. And then we have to figure out at each time frequency point which sound source is dominant. There's different assumptions made in the literature. For example, one of the popular assumptions that assuming that one of the each time frequency point is dominated by one particular source. This is a sparsity assumption. Then we can estimate the mask, which shows the probability. Each time frequency point, at each time frequency zone, each source is dominating. We need to estimate that probability. And there are both binary mask and a soft mask, which has a value between 0 and 1, can be applied. And then how to estimate the mask, we can use some of the informations which we can estimate from the signal. For example, this onset, offset information, periodicity, and harmonicity, and locations and spatial cues. That type of information could be used to help you estimate the time frequency mask. And I just show you, earlier demo. This was provided by Professor Donian Wang from Ohio State University, where you can see that if you can estimate the time frequency mask, you could really get a very high quality or intelligibility sound. Here we have these mixtures of, this is a mixtures of two speech sources.
Only the best players enjoy popularity.
And then if you could estimate the time frequency mask, here we're talking about idea binary mask. Binary mask means that the mask has a values either 0 or 1, right? 1 means that the sound source is present or dominating at that particular time frequency point. If you apply this mask to the mixture, then what you get is something like this.
Primitive tribes have an upbeat attitude.
So that's clearly show that you can actually separate the target sound from the mixtures if you can estimate the time frequency mask. But the question is how to estimate that. There are a lot of papers out there telling you how to estimate them using the information from the signal, or based on certain assumptions or constraints. Here I show you one example, which is for binaural speech source separation, where we have two microphones, X1 and X2. And then you could use the information, for example, interoral phase difference and interoral level difference to determine, each time frequency point, how we should allocate to which source. So based on the information, we could use some techniques similar to clustering, right? And we can figure out actually the assignment of the time frequency point in the mixtures to each individual sound sources. So that's the spatial information we are considering. This information can be estimated from the microphone signals, a pair of microphones. If you have multiple channels, then you could potentially extend these techniques to multiple channels. I think there's a paper by Professor Paris Smaragdis extended this to multiple channels using the features similar to IPD and ILD, but considering multiple pairs of microphones. That's using the spatial information. Of course, you can also use other information like a common amplitude modulation. There is a single channel information if you have some mixtures early from single channels. But the challenges that when we separate the speech sources is, one is you could have this acoustic noise in the background. Another one is room reverberations, as you all know when you study this area, right? And with the presence of the acoustic noise and room reverberations, the estimation of the time frequency mask becomes very challenging, which means that the errors will increase if you have increased the level of room reverberation and acoustic noise. And what happens is that, for example, if you have the sound sources like the top two figures, and depending on how accurate the mask is, you might get the estimation like this, that there could be still a lot of interference there in the estimated speech sources. So a lot of papers there talking about how to improve the quality of the time frequency mask estimated from the mixtures. And here we try to introduce techniques which recent years a lot of people have further studied this in both signal processing and computer vision communities. Before, I think there's not much work from computer vision community, but the recent few years, there's quite a few papers from CVPR. They also considered this problem. So we humans actually have the ability to perceive sound, not just by listening to the sound, right, but also looking at the movement of the lips, especially for hearing impaired or deaf people. So that's the idea. So potentially we could use the lip movement information to help us perceive the sound better. So that's the idea of an audiovisual speech source separation. Actually, this idea initially was applied to speech recognition, where people have considered using video information to improve speech recognition performance. And but for speech source separation, we only started around in I think 2002 or 2001. So it's a pretty early work started from then. So this is basically using try to model the dependencies between audio and video, and then try to incorporate such information either as constraints or as regularization terms in source separation. You know, when you do, for example, optimization and learning, you can incorporate such information to either help you improve the mixed metrics, or help you to solve some of the challenges in the conventional source separation. And here are some earlier papers. If you want to know more details, of course, later I will show you also some recent papers in this area. So the motivation is we try to build the dependencies or coherence between an audio and video signal. And there are probably many applications out there you can consider where you have both cameras and microphones, which you can estimate such information to help you. Potential use cases where you have the you phone somebody using your mobile phone, and then if you hold the phone in this way, then the camera might be facing towards you. So then the camera can read the lip movements. This is particularly useful if you're in a very noisy environment where you have a clear information from the lip movement. That could be very useful. So the key challenge is how to build the audiovisual coherence or audiovisual dependencies and how to model that. Another one is how to incorporate such information into the separation system, right? And of course, when we model the coherence, we also have to consider the difference between the two modalities, or in terms of the size, dimensionality, and the sampling rate, and such problems. And here we give you two examples to show how potentially you can model the audio-visual coherence. The one is based on the conventional technique. Essentially, is we are considered Gaussian mixed models, where we try to extract visual features from video signal. For example, here we can extract the nip area, and then we can capture the nip contour information, the inner contour and the outer contour. And this could be used as the visual features. And the acoustic features, you can use many acoustic features, for example, the classical MFCC, or you could use Meyer spectrogram and some other features you could use that. And then you can build this joint audiovisual feature space. And you can also perform feature selections if some features are corrupted by noise, and you can actually improve the feature representations. Once you get these features, you can then use some models. Here we talk about the Gaussian mixed model that we can actually, this is audio feature A and video feature V here for example, time frame M. And depending on how many Gaussian kernels you're using, and you can actually build this, this is the model we can use to categorize the relationship between audio and video. So here we show some examples. If you use this to model some of the phonemes, for example, then how would you get in terms of the feature representations? And that's the contour information you might get in terms of when the humans pronounce these different phonemes. And then you can use this information in the, for example, conventional source separation algorithms. Here we show you this frequency domain speech source separation, where we convert the speech sources into the frequency domain using, for example, a short time Fourier transform. And then you can perform source separation for each frequency component using independent component analysis, which we can actually estimate the individual source component S1 hat and S2 hat. That's the estimated version. But one of the issues with the conventional ICA technique is that there's a so-called permutation and scaling ambiguities, which means that the order from the output of the ICA could be random. This is S1 and S2. This might be, for example, S2 and S1, right? This could be S2 and S1. So these two orders are not consistent. So you have to determine, okay, whether this one should be put together with this one or with this one. You have to decide this when you put together the source, estimated source components together. Otherwise, the speech sources reconstructed might be still very noisy, containing the interference sound. So here we show that using this audiovisual coherence, we could potentially help you correct the permutation inconsistencies. This is the conventional frequency domain source separation architecture, where you use ICA techniques to separate, and then you perform permutation alignment, and then you apply inverse time frequency transform, and then you can get back to the sound sources of the original speech. But here we try to incorporate this, this information, to help you improve the permutation corrections based on the audiovisual coherence we modeled using P here. Yeah, that's the general idea in terms of how we could use this in a conventional speech source separation system. And how to solve the permutation? Here we have developed an algorithm. Is a iterative sorting scheme where we can, we actually maximize this term. This P here is the permutation matrix. We try to maximize this term. Essentially, is the coherence between the source component estimated at each frequency bin. We want to do the matching. Yeah. So here, this is essentially is we have a copy for the estimated speech source. We try to match them at each frequency component, and based on this criterion, and we see which one gives you the maximum probability. If we pick up that one, and then we reshuffle the orders of the speech source component. So actually, I have a demo. I don't know whether I can play here. That actually shows how we corrected the permutation. This is different colors means for different sources, right? And we try to use the audio-visual coherence to help you align the frequency component from the different sources. So, okay. So this is one idea, and then another idea is using so-called audio-visual dictionary learning. Dictionary learning is sparse representation is a technique which has been widely used for many signal processing problems, especially for signal representations in, for example, in compressed sensing and, underdetermined systems, right? And here we show that using these sparse representations and the dictionary learning, we could also build the audio-visual dependencies or coherence. This is learned implicitly. It's different from the one we just discussed. We try to model the coherence using the Gaussian mixed model, but now is we try to build a audio-visual dictionary, which can then you can actually map the audio and visual streams to the dictionary, and you calculate the sparse representation coefficients. That actually helps you to generate a time frequency mask, which can help you to separate the sound sources. This is the diagram. What you could do is this is a conventional source separation system, and you can actually, if we use a time friction mask, as I just explained, then you could use this visual information to help you improve the mask. How to do that? We have a little bit more information next. So this is a conventional technique, for example, and what we will try to do here is we use some training sequences, audio, paired audio-video data, and then we can build the audio-visual dictionary. This is one example of the audio-visual dictionary, which you have this NIP movement. This is a sequence of images captured from the NIP area, and that's actually the sound, for example, the word, and this can be also captured from the audio signals, and you can actually build these joint representations. You have multiple such atoms in the dictionary, and so dictionary learning is a standard technique now in signal processing. Basically, the idea is that given some training examples, each column vector is a training example. It could be image, it could be sound, right? Depending on how you represent it. If the sound is just a short audio segment, if it's images, it could be, for example, 8 by 8 pixels. You reshape to a column vector. And then you have a dictionary, which is just the atoms signal component that you want to represent your signal, right? Here, X are just the sparse coefficients. This is a overcomplete kind of system where you have some redundancies in terms of the sparse coefficients. You have a lot of zeros here, only a few non-zero represented as red here. So that's why we call it sparse, right? And how to, so the question is how to obtain a dictionary from training signals, with unknown coefficients, right? So often we do this by using this iterative process. You take the signals. Initially, you have a initial dictionary D, which you don't know you could initialize randomly, and then you find the sparse coefficients, and then you update the dictionary atoms. There's many techniques available there. For example, KSVD or gradient descent. You can optimize that. The cost function could be, the reconstruction between these two, y and dx. You just subtract them. That could be a cost function. But often we apply some constraints, like sparsity constraint of x. But here we actually apply such ideas to audiovisual dictionary learning, where we have audio and visual component, right? For example, we could use KSVD to learn the atoms of the audio part and the visual part. We could use. I mean, these two techniques, even though they're different, but it's actually there's a paper discussed the relationship. Essentially, this could be considered as a generalized version of key means. But it's just, the level of sparsity can be different, can be controlled actually. So this is following the similar process. This is sparse coding, and this is a dictionary update. You go on and on, update until the algorithm converges. And finally, you will get a dictionary which is optimized from the training data. So by building this, then we can actually get such audio visual atoms from the training data. This is just one example here of the audio visual dictionary atoms. So now how to use this in the speech separation system to improve the speech separation quality. Here we consider one option is to improve the time friction mask in the conventional speech separation system. And basically, we are using this visual information to help you reconstruct the audio data. So it's essentially, because in the sparse representations, we can actually consider how good is the dictionary learn, and then we can use that data to reconstruct the signal. And we can actually generate a so-called visual mask. And using this visual mask, we can regularize or modify the audio mask, audio time frequency mask. Yeah, but this is just one option. Potentially, you could have other options. I show you some examples here. Here is the original unknown speech sources, and these are the microphone signal, the speech mixtures. And here we show that the visual mask we generated and the audio mask. And then this is a compilation of audio-visual mask, and this is an idea mask, actually. Idea mask is assuming the demo we just explained earlier. So you can compare how similar between these masks and the idea mask, because the idea mask could be considered as a performance benchmark for this case. And we have also examined the general performance by also comparing with some other techniques. For example, this is a, I think this is this is an early technique. I just showed the ICA techniques based, you incorporating audiovisual information. This is the proposed one here for using the dictionary learning. And this is a audio-only system, right? And this is using visual mask only. So you can see that by incorporating the visual information into the speech separation system, you can improve the performance for noise-free case, and also noisy case. This here we have noise at 10 decibels. So this is the performance. Of course, we have more experiment in the paper. Just here we just show you. Now I play with a sound demo. This is the sound mixtures using the impulse response captured in the real room.
List frigates in China's sea and in destinations.
Tonkin is nearest to Sacramento.
So it's very, actually there's a noise there. There's added noise there. And here is the result.
Which ship in Gulf of Tonkin is nearest to Sacramento? Which ships in Sea of Japan have a harpoon capability?
There's still interference there, but it's attenuated. And we have also compared with other techniques there. And this is a pretty challenging case because the room is a real room, and also we have added background noise there. But of course, the result is published more than 10 years ago. But now
list frigates in.
Now actually there's a lot more development in the literature. I'll just show you this is a slide I borrowed from my former postdoc, Dr. Yung, now works in Tencent in US. And this is the table they created in terms of the recent development in speech source separation. And you can see the trend. In terms of the input, it could be a single channel audio, which is a single speech mixture. Could be multiple channels, multiple microphones, and also multiple channel and multimodal. Multimodal means audio visual, for example, or even some other sensors as well. And if you look at the system, before we often perform these tasks separately, like separation, beamforming, diarization, or ASR. But there's also papers, try to develop this end-to-end system, which is able to perform multiple tasks simultaneously without having to develop individual systems for each task. So anyway, if you're interested, you can read these recent papers. And here I'll show you this is the information when I review what happens recently as I come across these data challenges. This is a chime challenge. You probably know if you work on speech recognition, that's been there for a few years now. This is the MISP challenge, which is the audiovisual speech separation challenge. And you have some other data set which are suitable for this study. For example, this AMI, meeting environment. This is another one, M2 MIT data set. And I just got to know another data set. This is from Meta. It could be very useful for especially the ego-centric scenario we will discuss later. That's also for speech source separation, but the cameras and microphones are mounted on the glasses. And some other interesting development I think might be interesting to you. One is this is some new development where they use deep learning systems for building the audio-visual dependencies, and then general sound separation. Just now we talk about speech separation, but there's also increasing interest in the community. They want to separate, general sound. For example, dog barking, footstep sound, gunshot sound, whatever, based on audio and video streams, right? Universal sound is more like that. You try to separate any sound, not just the speech and the music, but could be anything. And there's also recent interest in terms of language guided sound separation, speech separation, and universal sound source separation, where you use text prompt and then ask the system to separate a particular sound sources you want. And even for sound source localization, I noticed there's work there now. Using the text description, you can tell the system, which sound source you want, where from which direction, for example. This is called language guided universal source separation, and also there's work. You can see that language guided audiovisual sound separation. So that's a very interesting development in the literature, and you can see that many papers are published on CVPR, ECCV. That's not from signal processing community; it's from computer vision community. They pick up the work and then they do a lot more recently. Yeah. So yeah, I think I'm conscious of time, and so another very relevant task is multi-speaker localization and tracking. That's actually, if we show you the video here, then it's like in this type of environment. If you have a robot, you want to understand, this type of environment where we have multiple people moving around and might also be speaking simultaneously, and how you able to estimate the number of speakers in the room, and also where are they in the room. So potential applications, for example, human computer and robot interaction. And you may also have other applications, for example, video conferences. There's one data set like that, and surveillance type of applications. And I mentioned the major challenges in this problem. And so basically, there are quite a lot of challenges there. For example, misdetections. You have unreliable measurements when you estimate where the targets are and how many they are, right? You have to use some measurements, either from video or from audio. But measurement are often corrupted by background noise, or the video measurement could be corrupted by illumination changes or occlusions, for example. So this actually lead to these problems like misdetection, occlusion, noise, clutters. And also this number of speakers unknown could be changing over time, and how to reliably estimate the number of speakers in a room environment. That's also a challenge. And the speakers' orders, for example, how are you able to associate the measurements with the speakers? For example, the speaker's appearance might be changing, and that's also an important challenge. So in terms of the work we discuss here, we are basically using visual cues and audio cues extracted from visual measurements and audio measurements. If you look at the advantage and disadvantage of these two, for example, visual measurements the benefit is that normally the measurement noise is lower if you compare with sound, because the sound can be easily corrupted by the background and the interference sound from the background. But visual cues, often you have a limited tracking area depending on the camera view, actually, and also can be affected by the occlusions and the illumination changes. But acoustics, is easy to easy to distinguish occluded speakers, because that using the microphone arrays, you can potentially have a better estimate. And also, is not so limited by the field of view, because the microphones can hear the sound from 360 degrees if you use omnidirectional microphones. But the problem is the measurement noise. And so here we consider, modernity diffusion, which we can partially address the problems we face. And if you look at the methods for multi-speaker tracking in the signal processing community, these are popular techniques. For example, you have a joint probabilistic data association filter. You have this multiple hypothesis tracking filter and a random finding set. And each method has, pros and cons. I won't discuss in detail now, but I just want to here we briefly explain the idea of a random finding set. One particular example is a PhD filter, probability hypothesis density filter, which is sample particle-based techniques, where, for example, we the first step, there's no equations here, but if you want the complicated equations in the papers, but here just explain the basic idea. For example, if you start from somewhere, let's say last frame, where you know that this is your estimate of the positions of the target, and also the initial state of the particles. The particles are essentially just a noisy version of the estimated state. When you do it step by step, each time step, right? And then if, for example, the target, the real position of the target are cross here, then what you do is actually you need to estimate the for example, this is the prior density, and then you can distribute the particles, update the particles essentially. You can figure out where the particles should be, and also the weight for each particles. Here, the size of the circle here means how big is the weight. The bigger means the higher weight, which means that the more likely the target will be at that particular position. So you can then, estimate the. Sorry. What's happening? Yeah, then you calculate the likelihood density. Yeah, that actually from the measurement, right? Given the let's say the likelihood you can calculate from the measurements, and then you can update the particles. So the updated particles here means that the weight of the particles and also the state of the particles will be updated. The state of particles has the positions of the the target. Sorry, why? Oh, I forgot to plug in the. Go on. Yeah, it's here. Okay, sorry for that. And then you can actually cluster the particles, and then you can, cluster particles that give you the estimate of the potential positions of the target. And then, but after the step, later on we will explain there's potential issues of so-called particle degeneracy. And so that we often use another step called particle resample particles to help you mitigate that issue. And then you can go back and let's just iterate between these processes. Then you can estimate where the target are. So PhD filters, they have, for example, the different versions. One is Gaussian mixture PhD. Another one is sequential Monte Carlo PhD. So here we actually, the example we showed just now is sequential Monte Carlo based PhD. So you can see the difference between them, right? They have advantage and disadvantage between these two methods. And now I show you another example where how if we apply this to audiovisual data. Here we are using the data from AV 16.3, which is used in a number of papers for audiovisual speaker tracking. Basically, for example, here we have two speakers where you have these, in the positions of the initial particles and the position of the target. And then essentially what you do is you need to relocate the particles. Here we're actually using audio information. We can see that in AV16 you have the microphone arrays on the table. And using the audio signals, you can potentially figure out the direction of arrival of the speech sources. And then you can actually then update the particles, for example, calculating the likelihood based on the measurements. And then you have you can update the weight. And finally, you cluster the particles and you do the resampling. This is the same process as I just explained for the simulation example. But there are limitations for this technique. One of the major limitations is so-called weight degeneracy. Here I'll show you what it is. For example, after the update step, you update the particles. After update, some of the weight might become very big. And some of the particle it has very large weight, but some of the particles very small weight. Very small weight might, tend to be neglected and less important. But after a few iterations, you may get only a very small number of particles. So you're not able to carry on iterating this process. So here we have a technique that is called particle flow to address this problem. This is how we do in the conventional PhD filter, where you have this prior density, and this is likelihood density, right? And this is the blue ball are the weight of the particles. And after this prior density, then you get this, for example, you consider the prior and the likelihood, and then you get the posterior. That's the posterior get. Yeah, you can see that the number of particles has become smaller, and also only a few with significant weight. Yeah, because a bigger board here. That's not idea for if you want to carry on iterating the process. So what here we propose is so-called particle flow techniques that can help you to mitigate this issue. How we do that? Basically, before you update, with the likelihood, before you update, we perform a so-called particle flow stage, which help you to move the particles, towards these likelihood densities. And we use these differential equations to do that. So now you can see that after you consider this prior and likelihood, you get a posterior density, which looks pretty reasonable as compared with this one. This one, you get only a few particles. So that's how we do. And this is the process. I have limited time, so I run quickly. So what you do is you select the particles, you calculate the variance and means and variance, and then you update the particles based on so-called particle flow. This is a differential equation. Basically, you estimate the direction where the particles should be moving, and then you can update the particles, and then pseudo time. Here we call pseudo time. We use multiple steps to to move the particles. I here also have a little demos here to show roughly how it works. Yeah, so that's we call particle flow, right? It's actually we push the particles towards their posterior density area. So that's how it works, and I don't have time to cover all the details, but just show the brief process which we is mainly changing this step, update step. This is the conventional particle PhD filter, but here we incorporated the particle flow where we use this particle state update that give you a better estimate of the speaker state and the target speaker state. So we use this data set, we evaluated the performance and using OSPA, that's the popular performance metrics for multi-target tracking. We evaluated in both AV16 and also locator dataset, which is the audio-only dataset. Now this is a result. You can see that there are some improvements if you use the particle flow as compared with using some other techniques. That's actually that tracking accuracy using OSPA. Next, I show you the demo.
移动一下，你可以不拍照，你也可以那个刘主管说话，换个位置，你必须要说点话。好的。然后呢？那你不应该。
So here actually is in the recorded in the lab environment where you can see how the particles are changing when you have multiple speakers. Here we have both camera and microphones, which you can see. The demo is longer. We consider both misdetections and clutters. You can see if you're interested, you can play here later. We can see that. I think there. Oh, sorry. Oh, anyway, there are other scenarios, but because of the limit of time, so I just quickly comes through to the ego-centric scenario. Ego-centric scenario is the work we studied only a short time ago. So in ego-centric scenario, the audio and video measurements are taken by cameras and microphones mounted on the body, and is moving, could be potentially moving rapidly. So in this case, it's becoming much more challenging. Here is the example from AV16.3. Is not that challenging. Of course, the illumination could cause a problem. But for this is simulated data, there are real data collected by Meta company. You can see that in many video frames, you might not have the target speaker, which means that the camera is not looking towards it, because when you're moving your head, if you use a robot, you might have a similar scenario where the robot is turning the head around, so it's not really looking at the speakers unless you're looking towards the speaker. But otherwise, you get the image sequence like this. So many frames that they don't have the speakers in the view. This is one of the big challenge. So we have recently performed some initial studies using this transformer-based architecture. And we also did experiment on this real data set. Is the easy comb data set. Some of you might be using that. But the other data set I mentioned released by Meta could also be useful to study this scenario. Here we have some very initial experiments where we use a transformer-based system to fuse the audio-visual measurements. That's the estimate you get. So sorry, it's very brief. Have to conclude now. Basically we have discussed a few topics: audiovisual speech source separation, multi-speaker tracking, and ego-centric scenario. But you can see that there are many challenges out there. Going forward, I'm particularly interested in some of the topics for example, ego-centric scenario, how to deal with these high percentage missing measurements that's likely to happen in the real scenario. And the prompt-based source separation is something I'm also quite interested in. We have a PhD working on that, actually. And this visual text prompt speech separation and also extending to universal sound, not just speech, but also some other acoustic event in a room environment, that could also be very interesting. And thank you very much for your attention.
Thank you very much for a fascinating talk. We have a few minutes for questions from the audience.
In the video you were showing at the end with the 3 students that were talking, on some picture you could see that you couldn't see the lips. The person was sideways, right? So how does it work? Because what you presented was the lips. We couldn't see the lips.
We are mainly focusing on the tracking of the speakers. So we're not particularly looking at the lips. The lips information was used in the the lips information was used in the audio-visual speech separation task, but not in this tracking task. In the tracking task, actually, here the visual measurement is, you can see that we are using the visual measurement from half of the body, that area actually. It's not just, in this case, you're right. It's very hard to detect the lips, and sometimes the face is not facing towards the camera. So yeah, that's pretty challenging to use that information. It's probably not that reliable, yeah.
But then you have the audio at the same time.
Yeah, we have the audio, yeah. And so also the...
both modalities probably could work.
Yeah.
Even if one of them is occluded.
Yeah, if we combine, it potentially could work. Yeah. So... I guess the how to reliably use such information in the audio-visual dependency when we incorporate the information into speech source separation. Yeah, there's still, I think there's still scope to further study that. Yeah, especially in the the recent activities, people have considered some other techniques to try to improve that modeling. Yeah, modeling of audio-visual coherence in speech separation. Yeah.
Was it another question?
That over there. Yeah.
Switch. We have to switch. No. This is what you were saying.
Thanks for the talk. So I'm wondering, do you think there will be soon a deep learning revolution where I guess the problem I see is maybe the data, but do you feel there's something else that might stop that, we just have a big model, we just have data, and all these problems are kind of solved by Google or OpenAI?
Yeah, I think the problem, as we have seen that today I covered mainly the conventional techniques, or we call single person statistical, or these conventional models rather than deep learning model. And later we also showed the deep learning the development. But that, as you pointed out that the biggest challenge probably is the build data set actually. And at the moment, I don't see there are many scaled data, or large scale data set which are suitable for training the system, especially if you want to develop a model end to end. And annotating a single video sequences already take a lot of time. And that's why we haven't got a good solution to address that issue actually. There are data sets published, for example, by Meta. But if you look at the scenario they considered is, some of them are pretty simple scenario, like for localization case, not really having multiple people moving around. There are also some existing data set out there with a few speakers moving. Sometimes only one speaker is speaking. These data sets are still pretty small. It's probably not suitable for building these large models like transformer models. And even you use that, the performance might be not as good. So I think this is pretty open, how to leverage the strengths of these learning-based models, but how to do that actually. In some tasks, it might be easier to build a data set. There might be scope to explore these self-supervised learning or unsupervised learning techniques to learn this directly from data without having to annotate so much data. Yeah, but I guess the temporal information here in the video could be a problem. The task is a bit different from the other task like classification, right? So I haven't got good solution for that.
I guess the hybrid system can do a lot of work here.
Yeah.
So part based on the model and part based on the data.
Yeah. There could be a way forward. Yeah. There's also increasing. Yeah. Text information could be very useful. Recently, we have been exploring that for some other audio tasks. There's a lot of potential there, but people haven't explored. For example, in sound classification, before we can give you an example like if you have a clock is ticking 5 times, that type of sound. And the conventional classification model can easily tell you, oh, that's clock sound. But it's not easy to tell you that's 5 o'clock, right? So, but now it become much easier to do that. You just, plug in the language model. The language model already learned the knowledge from textbooks, from Wikipedia text data that already describe how 5 o'clock sounds like. In the text information actually, even you're not hearing the sound, but they already teach you what 5 o'clock sounds like. Yeah, that type of information could be considered like reasoning from the language models, can be very useful for doing that. I mean, it's not explored yet by the community. I mean, there's potential there. And as Sharon said, that the joint models like data-driven model plus physical model or statistical model could be very useful. Recently, we have published another paper exploring that, where we is like a differentiable particle filter or PhD filter, where you have you have the particles updating based on some models, and then you use some measurement there. But this process could be improved by using plugging some data-driven models. Some part of these conventional models like particle filter or PhD filter can be improved using neural networks. Actually, there are a few papers out there that help you to do that. We also applied that for tracking, speaker tracking, but I didn't include that work here. But yeah, that paper is just accepted by IEEE journal. Yeah. So there's potential there to help you on that. Yeah. Thank you very much.
So thank you. For the sake of time, we'll have to move on, but you're still around so we can ask you questions. So thank you very much for a wonderful talk. Hi again. As I said before, my name is Sharon Gannot. I come from Bar-Ilan University. I'm part of the Spring project. I will very briefly talk about what we did in the project, and then I will try to focus on one of the algorithms, very recent one, that was just recently accepted for publication, and I will try to also discuss this. Okay, so in audio, in Spring we have audio-visual part, or maybe the perception, the human perception part, and we are interested in the detection and tracking of the speakers. So the fact that speakers are in the scene and to track them, so to localize and track. We are interested in extracting them. So if there are multiple speakers speaking concurrently, we would like to focus on one of the speakers. And then, of course, the ASR will be behind the system that extract the speaker or extract or separate the speakers in order to understand the conversation. We want to do this both in static robot and in moving robot. When the robot is moving, of course, everything becomes much more complex due to the fact that the entire scene and also the noise sources are moving with respect to the robot. So we have a bunch of algorithms that were developed for the project: noise reduction, narrowband noise reduction for the engine noise, single microphone speaker separation, single microphone speaker extraction, where we have some type of reference for the desired speaker, speaker identification, classification of the audio activity, multi-person visual tracking and audio tracking, and fusion. And we need boxes. So here are some. This is the box diagram. But today I will focus on audio-less audio-visual processing. So no audio. It's hard to me to say, since this is what I was doing for the last many years. But this is, we don't have an audio input, and we'll try to do something without it. So this is based on a work that was just accepted to ICLR, and together with students and colleagues. So what we are interested in, we see the visual. So we have a visual information, silent video, but we don't hear anything. This can be due to the fact that that it's very noisy environment, or due to the fact that somehow the audio is lost, and we would like to recreate or regenerate the audio, but we don't want to do this just arbitrary, but we want to do this that will respect what we see. And what we see lip motion or lip movement, and we would like to be in line with the lip movement. Also, the sound that is produced should be sound natural and intelligible, of course. And what is very important as well, that the sound that is created or generated should match the visual figure. So if we see a young girl, we don't want a voice of an old man. So it should also fit this. So now it's even without video. So what we are using in this algorithm is something which is a new trend in generative model, which is called diffusion models. I will very, very briefly talk about what are the diffusion models. We use them in order to generate MEL spectrograms, which is some type of short time Fourier transform with non-equal bands width of the frequency band, and then we generate the audio based on this. We have the visual information, but we want to invent somehow text information in order to assist us, and this is what we'll explain how we do this soon. So let's start very briefly with what are diffusion models. So diffusion models are generative models. It started maybe 10 years ago, but gained a lot of popularity in recent years, or maybe recent year even, I would say. So there are a lot of works. So the basic idea is that we start with a good image. It started in image processing. It's a good image, and we gradually add noise to the image until we have just noise. And our problem is to get a noise, and from the noise to get back to the image. So to do the reverse of the of this there is a forward process, and we would like to see the reverse one, in which we denoise the signal gradually until we get back the new picture. Of course, we train the system, but in test time we don't have the image that we were trying to denoise. So this is a probabilistic problem. Actually, it's a diffusion process. The problem with the diffusion process, I'll get back here, is that we can calculate very easily the forward process, or the probability density function of the forward. However, the backward one does not work. So this is, if we look at the forward one, so this is when we are in time t or step t minus 1, we can easily go to step t by just adding Gaussian noise. So this is the noise. Here we add noise, so we can also calculate what is the probability density function of a single step based on the start of the process. If we want to go back, we can reverse the equations. However, we cannot calculate this. So this becomes intractable. And we can show, I don't show it here, that if we add also in the probability density function also we give the initial one, then it is tractable. But what we want to do is to replace this creature by a neural network. And the neural network, which is learned, the neural network will try to imitate this probability density function of the reverse process. We train this model using the KL divergence, which boils down, I would not get into the details here too much, boils down to this L2 equation, in which we have epsilon theta, which is the noise which is created by the network, and epsilon is the noise that we would like to regenerate. So we have, in training, we minimize this cost function, theta is all the parameters of the network, and in the sampling or the inference time, we have here a recipe how to denoise gradually the signal based on the previous step, and also on the epsilon theta, which is created by the network. Sorry that it's too fast, but just the details. However, if we are trying to do this, it goes rather arbitrarily. So this is why we need some type of guide, or we can make use of guidance. Guidance helps this process of denoising into the correct direction. So how do we do guidance? Usually in the literature, there is something that is called classifier guidance. So we have a classifier in parallel that tries to improve the steps. So the steps, rather than going based on the network, we also add another term which is related to the derivative of the classifier. So we try that the output at each stage, each stage of this denoising will be as close as possible to a cluster. So this is what we are trying to do. There are some more details which I'll skip. And now what we are doing with this in the project. So the problem is that we have a video. The video is silent. So what we take from the video, I'll explain a bit more details later, but in general, we take multiple frames of the video, only the lip area, since the lip is related to the audio generation, of course. This is heavily related, also when we talked about it. And also an image separately, one of the images from the movie, and this one will help us to generate the sound which is resembles the person that is that we see. So here we need a woman's voice. So what we want to do, I will talk about this MEL gen, but we generate the MEL spectrogram. The MEL spectrograms are very common features for noise, for speech generation in general. So we try to generate them based on the lip movement and the image. We start from a noisy spectrogram and gradually denoise. But where is the classification that we said? Where is the guidance that we can have here? This comes from an ASR. So ASR is automatic speech recognition. So we generate a sound. The sound should be intelligible by a machine. So we have an automatic speech recognition that is calculating the error rate actually for each of the denoise steps. In parallel, we have a lip reader that looks at the lips and also try to transcribe what it sees. And then the classifier guidance try to see if they are the same or not. So if the lip reader and the voice that it generated are the same. By doing this, we are trying to guide our generative model towards intelligible speech. By the way, this was something which was a bit amusing. When we didn't use this ASR guidance, then it produces a very nice looking sound. So the audio was very well fitted to the lips, but it was just gibberish. So the fact that we have the language model here helps us a lot in order to guide the system. So after we did this, we have these denoising steps. And from the denoising steps, we create the MEL spectrogram, and then this one can be used by regular audio generation system in order to create a sound. So if we look a bit about how we create, how we generate this MEL spectrogram, so we take the silent lip video, only the lip area. So we cut the lip out of it by some standard method. We take a ResNet from the image and replicate it for all time frames in order to create the sound that will resemble the person that is talking. And this one based on TCN and some more or less standard network. And then we take this one and use diffwave, which is a very common voice generation, in order to generate this this noise term that denoise the signal. I'll skip also the details. So I would like to talk a bit more about the text guidance. I said about it. We could use the text that is read from the lips. We could use it as another input, but we didn't want to do this. By doing this, it will give us a lot of constraint on the training process. Here we do this use of the ASR only during inference. So only in the inference time we apply the ASR to the denoise or gradually denoise signal. I'll skip some of the details for the sake of time, and I'll go a bit to the experiment. We use two databases, which are videos of few people, two people speaking. I think they were recorded from BBC sessions. There is LRS2 and LRS3, which is even larger. We tried several things. First of all, we went to this Mechanical Turk, Amazon Mechanical Turk, in order to verify how real people would like our generated audio. And we asked the people, it's done online. So we asked them for how intelligible is the speaker, how natural it is, and sound quality in general, and also how the lips are synchronized with the generated audio. So everything is important. We compare to some other algorithm. This is the ground truth. So of course, if these people would say that the ground truth is not good, then we take them out from the statistics. This is a common procedure. And we can see that our method gives better results in both databases. We also see that the generated audio has much lower, you can see the other competitors, so the word error rate is extremely high. I don't know why 1 to 100. This is strange, but it's very, very noisy anyway. And but you can see that the word error rate was significantly reduced. And also STOI is a measure of intelligibility, MOS is a measure of quality, and these two are measure of synchronization. Let's try to hear some sound. So let's start from this. So I'll play the ground truth, so the original audio, and then some other methods.
Here to give us a rundown of the greatest facial choreography ever seen on the box.
One of the competitors.
Please use the rundown of the greatest facial choreography ever seen on the box.
Another one.
It gives you the rundown of the greatest facial choreography ever seen on the box.
As you can see, the ASR is somehow working, and it's quite good. And this will also male sound.
It's all based on this 58-page report prepared for the European Commission.
This is related to us.
It's all based on this 58-page report prepared for the European Commission.
I think it's very intelligible, but still very bad quality. These are competitors. This is not working. And this one.
Well, it's all based on this 58-page report prepared for the European Commission.
It's even have a British accent, I think. So this is just generated from the facial appearance and from the sound. There are a bunch of other examples, also example in which we failed. I will not play them, but you can see in the website. And I think I will conclude here and open the stage for questions. Yeah, there is a question.
Hi, thanks for the talk. It was really good. I have 3 questions. So first one would be, from what I saw, you used only supervised training. Did you maybe think about unsupervised pre-training for your models?
Well, there is some, the guidance was unsupervised. So the guidance came only in inference time, so the text modality. But other than this, it was in a sense self-supervised, since we have the audio. We have the video with the audio, we cut it out, and then we try to generate. So this was in the training stage.
But
so we have the ground truth audio, the video with the audio.
Okay, but you had also the text corresponding to the audio, right?
No.
No?
No. This we did only in inference time, and we compared the lip reader, which is like a conventional lip reader, and the ASR from our generated sound. So we didn't have any text.
Okay.
In training time, no text. Actually, the guidance was not relevant in training time, only in inference. So actually, this was one of the reasons why we went to guidance this way and not as another input. Another input would need to have the text as well, or whatever, something else.
Okay, so the next question would be, you use diffusion models. Did you maybe try some other generative models like variational autoencoders or GANs or something?
Not in this work. I worked with variational autoencoders in localization, also in part of the project. Not in this work. Variational autoencoders are known for being a bit nasty when training them, and the diffusion models are somewhat regarded as more stable. But I'm not saying that we cannot use other models. The diffusion models are very trendy also. Okay. So this is why we also tried them.
Yeah, and the last question, so you used a classifier. Can you go into a bit more detail about what the classifier did? Like, did you use some k-means on what data and so forth?
The classifier is actually the slide doesn't say much. The classifier is just a CTC model. So you have a stream, text stream from the lip reader, and you have a text stream from the ASR, and we want to align them.
Connection is temporal classification,
yes,
right?
Exactly.
Okay.
And so this is what we did. So this is the classes. So, but this one is, of course, you can also calculate the derivative of this, and so it's trainable. So this is what we used. So in a sense, we invented the classifier from the external to the entire system. It's based on the lip reader and the ASR which is generated. We didn't start with the ASR at the first stage, which was very noisy, and then it couldn't do anything. We gradually added the ASR during when the reverse diffusion progressed a bit. So the sound was already quite okay. Then we used the ASR in order to guide it. So before this, it was just the regular diffusion process.
Okay, thank you.
Thanks a lot. That's super impressive. I'm going to ask the question now. Is it speaker independent, or how much specialized is it for each speaker? It sounds so amazing that you must have trained it on that speaker to some extent.
No.
Or how easy is it to train? Like if you take a video of me now, right? How evolved would it be to make the same happen for me?
Well, first of all, it's a huge database, this LRS. Both of them are huge. The LRS tree is really huge, and we don't have all the person did not appear in the training. So these are only tests. The test people are different. It's a different test set.
So these are people that have not been in the training set.
Exactly. And now
I'm blown away. I mean, because they're clearly their voice sounds like the characteristics. How can it infer what sort of how these people will sound like in the turn of how they intonate? That's the thing I don't get.
Well,
how can you explain that?
You want to synchronize with the lips, so this is somewhat related to intonation, but like the accent, it looks at the face somehow and try to infer the accent, which is a bit weird, but this is what I think it is doing.
Okay.
So you have we took the video and we extracted one image and the lip area.
Okay.
So
but if you could do a demo of that system, I stand in front of it. We take the microphone out, and I'm not. We cut the microphone out, and it will make a voice in my tone.
Yeah, but not your own voice.
Can I ask for a demo, please?
No.
Why? Why not? No, why not? Why not? I mean, I'm really curious to see what's the difference.
I would say two things. First of all, I cannot make the demo, but I can ask the student to do this. This is one thing. Another thing, I don't know why, but sometimes neural networks are nasty. So you train them on a database,
right?
And then you go to another database, which is just database, and it fully collapses. So I don't know why.
Yeah, okay.
But we have a lot of this transfer learning or whatever we need to do, but they are somewhat sensitive. I also worked with simple discriminative model for source separation, tried on one common database, wow, 20 dB SIR, moved to another database, minus 25, without anything. For me, it sounds the same.
Okay, so
the systems are finding something.
There's no transfer learning, no retraining or post-processing for this specific people that we see. Wow.
Yeah.
Okay.
But we should try, of course, what you're saying. What we are doing now, it's not fully ready yet, is to add the audio, since I'm audio processing person. So if you'll add this mixed audio as well, then you have a very strong guidance from the sound itself, of course. But then we want to separate sources. So this one is it's not separating, it's just generating.
Cool.
Thank you.
Well, there are many questions. We have time for one more. So I'll give the floor to...
Actually, I had the same, but I just to mention that there are... I tend to agree with that because I have seen some works that they can make, due to the characteristics of the physical characteristics, the network can deduce the way the voice, but I'm not sure whether that architecture is was suitable or
yeah, we did resonate for the image, so the embedding of the image was resonate. But I think from the face you can imagine how this person would look, but it might be different, of course, and it sometimes fails, but not a lot.
So we'll take one more question, and Alex and Victor, you kidnap Sharon after, okay?
Okay, I'll be here.
Just an ethical concern, but you said that the accent is determined by the face.
Yes.
Isn't that supporting stereotypes? Because like if it was an Indian face, they would probably have like a very stereotypical Indian accent, even if they were born in Britain.
Yeah, this is what I told my student. Exactly, it's a problem. I think generative models are a problem. Can create ethical problems anyway. But this one, you're right. But I don't know how to deal with this. But this is correct. So sometimes the person would sound like perfect English, although it looks Israeli. I don't know what to do with this, but it would generate something that looks similar to my face somehow. But you're right.
All right, so I propose that we thank Wenwu and Sharon again.